Hello and welcome to a course on grammar development with LFG and XLE that I'm putting online. In this course, you will learn how to implement a computational grammar fragment with an LFG, which is lexical functional grammar, a theory of syntax, which is also used for computational purposes. You will work in particular with the grammar development platform XLE, and you will learn also how to integrate finite state morphological analyzers into the grammars that we're building. There will be one lesson on that. And at the end of the course, you should be able to begin building your own grammar for a language of your choice. And I will give you several pointers to starter grammars, etc., which you can find on the internet. What you will not learn, very important, is the course will introduce basic concepts and standard analyses within LFG, but I won't have time to spend time motivating these analyses or delving into alternatives or what researchers have said about certain constructions, etc. I can only give you the really basics, the standard analyses for constructions. Everything else, if you need to go deeper into LFG, you will need to take a separate course on this. This will also be available online, or work through some of the relevant literature, and I'll be giving you pointers to some of that literature as part of the course. For the course structures, please see the accompanying file for a detailed course outline. In each lesson, basically, the way it's organized is that you'll have an introduction to the theoretical concepts, demonstrations about how to implement those concepts, a sample grammar fragment that you can work with. We don't ask you to start from scratch, and exercises working with a grammar fragment. The course topics will be giving you LFG basics and first steps in XLE, then things like very classical things like lexical rules, passives and other argument alternations, adjuncts, adverbs and adjectives, PPs, adjuncts and obliques, very important to be able to implement PPs, generation and the optimality projection. This won't mean anything to you, but it'll become clear as we go through the course. Complements, XComp and comp, something that LFG is very famous for, long distance dependencies and functional uncertainty. One thing that shallow parsers are very bad at, this topic, and that other grammar formalisms are also not as good as. Then pronouns, empty nodes, punctuation, how to deal with things like that. Then integrating a finite state morphological analyzer. And then a few further basic XLE features, such as using the shuffle operator for free word order, using variables for things like relative clauses, and then in a final lesson, outlook advanced features of XLE, which include things like integration of statistical preferences, complex categories, transfer system, restriction operator for complex predicates, etc. And with the last one, I won't teach you in detail how to use those. I'll tell you what the background is, what the idea is about how to do that, and point you to the relevant places where you can read more about it. Okay, but that'll be it. Now, coming to today's lesson, we'll start with a motivation, why deep grammars in the first place. I'll give you, in order to motivate that, I'll give you some applications, demos of possible applications that have been built over the years. And then I'll give you a little bit about XLE LFG Basics, and then I'll ask you to get started with XLE, get it installed, and do that as a practical part of the course. I will also tell you a little bit about the Pargram, which is the Parallel Grammars collaboration, in which a lot of these grammars have been built. Okay, why deep grammars, the motivation? So there's some applications that you can have, question answering systems. I'll show you some demos of that. Electronic lookup or in general digital learning resources, and I'll show you some examples of that. And these tend to be used in something that's called computer assisted language learning, or CAL, and I think there's a lot of scope for using deep grammars in this area. And in particular, I'll show you something that a PhD student here at the University of Constance implemented, translation system between Murryn-Putter and English. So you can see what in principle can be done. And then I'll talk a little bit about automatically annotated corpora, namely tree banks. Okay, so deep grammars, they provide detailed morphosyntactic information They include detailed information about dependencies within the clause, so things like what is the subject, what is the object, who did what to whom, who killed whom, who pinched whom, who read what, etc. Clausal complements, what did people think, what did people believe, etc. So they give you that kind of information. They also give you information about the tense, aspect, mood of a clause. Was it indicative? Was it a question? Was it in the past tense? Was it in the present tense, etc.? And things like person, number, gender, case, and which bits are modifying which other bits, which bits are definite, which bits are indefinite, all that kind of very detailed information. And LFG also provides detailed information about constituencies, so which words work together as a constituent and what the hierarchical relationships are in the clause. So most dependency grammars will not give you that kind of detailed information. LFG gives you that information plus a dependency structure. So it really gives you a lot of information. A very simplified example here, Mary wants to leave. What we have is it'll say what the deep grammar will give you. It'll say something like, there's an instance Mary, let's call it number 3. And Mary is the subject of a verb want. Let's give that verb the ID 1. 1 takes a complement, let's call that 2, that's leave. And leave has a subject, which is also Mary. So what we know now is that Mary is the subject of both want and to leave. It's acting as a subject for both of those verbs. It's a control construction. And we also know something about the tense, that is present tense, so that leaves is in the present tense. She wants to leave now. Deep grammars are usually manually constructed. This is one reason why they're hard to make, because you actually need to know a lot of linguistic knowledge and you need to know knowledge about grammar engineering. But that is something that I will be trying to teach you in this course. They are large multilingual grammar development efforts. 2 of them, the largest one that I know of, are the LFG program effort, which I will be talking about in this course. But there's also, with head-driven phrase structure grammar, several larger efforts, Lingo, Matrix, Delphine. So if you're interested in alternatives, go look at those. Okay, so let's talk about some applications. So one application are tree banks. As many of you will probably know, many natural language processing tools depend on linguistically quite sophisticated resources. So a lot of the machine learning approaches that you have depend on having these corpora be annotated in certain ways with part of speech tags or with other kinds of information. And one of the ways in which you can annotate them is with syntactic information. And since the Penn Tree Bank for English, this has become a very useful, it's become established as a very useful resource. So one of the applications that you can do with deep grammars is to take a corpus of sentences and annotate it with deep syntactic information, and then you will have a so-called tree bank or a structure bank. So they can be used to annotate this. This is a much better decision than to try to do it manually, which traditional tree banks like the Penn Tree Bank, they have been done mostly manually, but deep grammars give you a much more systematic way of understanding how you've made design decisions and where to put those. And you can also see this as a form of language documentation. So if you're working on languages for which not many resources exist, you can actually see deep grammars as providing a way of documenting that language in a very systematic way, with allowing to tap into resources in a much more systematic way than, say, a paper grammar, a grammar that's been written up as a book can. Because you can go look up sentences, different kinds of tenses, etc. in the grammar. Okay. Other applications include question and answering systems. And you can use deep grammars, at least that is the hope, to use deep grammars in sophisticated question answering systems. And I'll give you 2 examples here. One is not with LFG, it's IBM's Watson. I'm giving that to you because it made a big splash in the newspapers, in the online media, etc., etc. And that actually uses a dependency grammar, somewhat like the grammar that I will be teaching you to use here. So it has some of the same idea in there. And the other example that actually uses an LFG grammar is the Park Bridge system. And that led to the founding of a company, PowerSet, which was later bought up by Microsoft. So I'm giving you these examples because these are both examples of industrial strength systems that have been used in actual industry or are still being used in industry. So IBM's Watson, which is now apparently teaming up with North Space to go into e-commerce, but it made a spectacular debut playing against humans on the US game show Jeopardy! And I won't show you the clip here, but the clip is, you can find it very, very easily on YouTube. And my favorite one is entitled Watson Destroys Humans on Jeopardy! And these are the two humans he destroys, Ken and Brad, who are Jeopardy! Champions. So Jeopardy!, if you don't know, is a question and answer show where you get answers and then have to provide the question. And Watson won, hands down. That's Watson in the middle over there. You can see him there. Okay, so check it out on YouTube. It's well worth it, and you can read about the design of Watson for example, in this paper that I've given you here. But there's also material you can find elsewhere on the internet. It's IBM itself has documented it quite well about all the parts of it, also the information retrieval part, which was very crucial. Okay, now let's give you an actual example with LFG. This is PARC's Bridge question and answer system. PARC stands for Palo Alto Research Center, famous place in California, invented the mouse and things like that. And they put together a demo a while ago to showcase their ideas for a linguistically sophisticated question and answer system. And the system includes, like I already said, LFG grammars of the type constructed in this course. In particular, they used the large English LFG grammar that was also built at PARC. And it was built, I should tell you, over the space of 10 years. It's a very big grammar, very robust grammar, but it took a long time to build. A finite state morphological analyzer, which didn't take as long to build, and it's something they call an abstract knowledge representation system, or AKR for short. This is a type of semantic analysis, but they didn't want to call it semantics. And they've also integrated a number of lexical semantic resources like WordNet and other information from other lexical resources like VerbNet and ontologies. You can read about the system in, for example, these two papers, which I've given you here. They're easy to find on the internet. And here's what the demo looks like. I'm not going to walk you through the demo live. I've done some screenshots here. It's easier to do with this kind of media. What I should say is that this demo is extremely fast. So it runs, there's no waiting time for this demo at all. You can't see that with the screenshots, but that's you'll have to take my word for it. Okay, so what this is a very simple interface. You've got a passage up here, and I've typed in "a man vanished last Saturday." For this passage, this is just for demo purposes, but you're supposed to imagine that where it says passage, instead of there being one sentence, it would be the entire Wikipedia or the entire internet or whatever. So the idea is that the system actually goes through, does information retrieval, and then has certain, has parsed actually. So what PowerSet ended up doing, the company, is they actually parsed the entire English Wikipedia and had these available as structures that they could look up. So the idea would be that you parse something like this: a man vanished last Saturday. Then you ask a question about that: did a person disappear? And then what the system does is it evaluates the question with respect to what it knows. In this case, all it knows is a man vanished last Saturday. And it'll give you the answer down here. And in this case, it says yes. And why does it say yes? Because it knows through its lexical resources that person is equal to man, so that a man is a person, and that vanish and disappear are lexically related, and that they sort of mean the same, that in some instances they mean the same thing. So then it'll say answer. So the way it works, the demo, is you type it in here, you type it in there, and then you press answer, and you get your answer almost instantaneously. In this case, the answer is yes. And the system I find quite impressive because it has actually done a lot of work in the time that it gives you the answer, which is instantaneous. What it has done, so let's have a look. It parses each of these sentences. So I'll show you what the syntax is. So if you actually click on the syntax button, what happens is that you get this kind of thing. you get a tree structure. It's called a C structure in LFG, where you can see the various constituents. So you can see a man is an NP, and you've got a verb phrase which consists of vanished last Saturday, so a verb and an adverbial. You can see the hierarchical organization. You can see various other things. What you can also see, if you click on a further node, if you look at vanished, that is actually, you can see that there's a finite state morphological analyzer that is feeding into the grammar. Okay, so where it said vanished before, right, there it just says vanished. If you click on that and ask to see the morphological analysis, what it'll give you this thing. So vanished is actually pretty printing for information that says there's vanish as a base, and it's a verb, and it is used in the past, and it can have all kinds of person and number markings. So English is not very big on morphology, so you don't have that much information. But each of these words is actually being fed through a morphological analyzer, a finite state morphological analyzer, and you're getting that kind of information. So, and I'll be teaching you how to do that yourself in one of the lessons. So you have all that in there. And in addition to that, to the linear order and the constituency structure, you also get something called a functional structure in LFG, or an F structure. And this provides dependency and other deep linguistic information. So what you've got here, a man vanished last Saturday, you've got the information that there is a main predicate vanish, its subject is man is indefinite, and it's singular, third person. What you have information about the clause is that it's declarative, not passive, indicative, and that it's past tense. And you also have information that it's modified in some way, that there's an adjunct, there's a weekday, Saturday, and that the time was at some point last Saturday. So Saturday is modified by last. So you have all that information in there. And this is the kind of information that you can then use to construct a semantics, or to understand the semantics. Okay, so you have this syntax. You also have parsed the question in the same way. So let's look at that just so you can see how that looks. Did a person disappear? What you get again is a tree and an F structure, and I've put these side by side here so you can see them. In this case, you see it's a question mark, and you also see that the grammar actually parses the punctuation. I'll be teaching you how to do that too. That's necessary in computational linguistics. And in this case, you see that the clause type is int, that stands for interrogative. It's indicative again, it's past tense again. What you also see is you have a main predicate, disappear, and the subject of the main predicate is person, and the person is again indefinite, and third person singular, etc. So you have all that as syntactic information. So the F structure that you just saw provides the input for the semantic analysis, this abstract knowledge representation. And F structures have actually been shown to be equivalent to quasi-logical forms, so they're basically already a good approximation of semantics. What you do is with the AKRs, you integrate lexical semantic information from WordNet and other sources. And then what the system does, it compares the AKRs of the two sentences to see whether you can say yes or no as an answer. Okay, so here's the AKR for a man vanished last Saturday. I'm not going to go through it in detail, but you can see that there's various concepts: weekday, Saturday, time period. That's a time period. You have a concept vanish, and this is the crucial bit. So you can see that vanish is related, this is WordNet information, to a reading disappear 1, reading vanish 2, fly, and several other vanishes. And the disappear one will be crucial because that's used to relate to the disappear of the other sentence. And then you have also information about man being could be a serviceman, a homo, a valet, and other kinds of man. And somehow in here, through the WordNet hierarchy, you also get to the fact that a man can be thought of as a person. So you have this kind of information here. Here's the AKR for did a person disappear? So here's the disappear reading. So disappear 1, that's the same one as we had before. And then we have the subconcept person, which at some point also points to man. So it compares these facts that it has gotten, and once it has compared these facts, it realizes that in fact they're compatible and that the answer can be yes, person is equal man, disappear is equal to vanish, and that's how you get the question answering done. But you've involved a huge amount of linguistic information, you've involved morphological information, you've involved syntax, and you've involved dependency relations, which you've translated into kind of semantics. You've involved lexical resources, and from that you can decide whether a given answer is a question, a given answer is the right answer to a given question. Okay, I'll show you some more examples of this in this system. You can ask something like, the president believes that Iran has some uranium. This was programmed during the Iran crisis. And then you can ask the question, does Iran have uranium? And the answer in this case is unknown. And that's correct, because the president only believes that Iran has some uranium. You actually don't know whether that's true or not. On the other hand, if you use a verb like know, the president knows that Iran has some uranium, the system will tell you yes. So it makes a difference between different kinds of verbs, whether you believe something, whether you know something, whether you think something, etc. So it's very sophisticated in that way as well. It also knows about negation. Sandy knows that Kim is not coming home, and you ask the question, is Kim coming home? Then the answer will be no. So it knows about negation as well. Not easy to build into the system, but the part people did it, and it works very robustly, this part. Another example, the destruction of Carthage occurred in 149 BC. Question, was Carthage destroyed? Answer, yes. Now, if you look at this is an interesting example because it's not doing just pattern matching, right? It's not doing just verbs, etc. I showed you how the AKR works before. But what it's doing here, it's actually showing you, it's taking the noun and it's understanding that this noun is related to a verb and that this verb has an agent and a patient, and that the patient is Carthage in this case. We don't know who destroyed it, but we know that Carthage was destroyed. It's the object of destroy. And this information is taken and used to try to understand the question, and what we have then is we have the question. This is a passive, was Carthage destroyed? So it knows about passives, it knows about nominalizations, and it can actually match these two things together. And this is quite impressive. Very, very few systems can actually do this way. And this is what deep linguistic information gives you, rather than just trying to do keyword spotting or very, very shallow processing. Okay, so that was that demo, the question answer demo. Like I said, they went on to found a company that was then bought up. Very, very good technology, very sophisticated technology. Here's a different kind of an application that's possible. It's again based on the large English LFG grammar that was done at Park. But in this case, we modified the grammar, and this is work, you can read about it in that MSc thesis, but it was work done together with Tracy Holloway King, who was then at Park. And together we modified the grammar, the LFG grammar. She's the one who built the LFG grammar. And we modified that grammar to parse ungrammatical sentences, to register, not only register, but to also communicate the type of ungrammaticality, and to generate a grammatical version of the ungrammatical sentence. So here again is a demo. What we've done here is we've parsed the sentence Sandy, very pretty and clever. These are sentences that were taken from a corpus of Chinese learners of English. And these are very typical of mistakes that Chinese learners of English make. So one thing they do is they leave out the copular be, because Chinese does not actually use it in the present tense. So something like Sandy, very pretty and clever is perfectly good in Chinese. It's not good in English because you need it. What the grammar does, it allows this structure to be parsed, but it does tell you it's ungrammatical. And then it also tells you why it's ungrammatical, right? It's telling you here ungrammatical, missing be. But all the other information is there, so it knows that the subject is Sandy and that there's certain properties of Sandy. She's pretty and she's clever, and it's present tense, and it's a copular verb, and it's a declarative, etc. So there's certain information, there's all the information you need is already there, and you've got the information that it's actually an ungrammatical sentence and that the be verb is missing. And when we did this is just within XLE, but what we thought is you could actually build a web interface and then give students that kind of feedback through a nice web interface. And another student of mine did this for Russian learners of German, and that worked actually quite well as a nice web interface. Okay, here's another example. The books is mine. This is ungrammatical. Why is it ungrammatical? Well, subject-verb agreement is the problem, as it says down there. So again, the grammar will parse it, but it'll register the fact that this was actually a bad sentence, and it'll tell you why again. And again, you've got all the information. You've got books as subject, and there's a certain type of thing, etc. Okay, another one. They hope graduate in June. Again, ungrammatical. Why? Because there's an infinitival missing too. But again, we have all the information. They, subject is a pronoun, plural, third person, etc. And what are they hoping to do? Well, they're hoping to graduate at some time in June. Okay, present tense, declarative, etc. Okay, so we've got all that. So what we've got so far is we've been able to tell people the sentence you put in is ungrammatical, and we've been able to tell you why. Okay, and this has been, so far we've only seen the parsing capability of the grammar. But all LFG and XLE grammars can use, so all of the grammars can be used to generate as well. And this is a unique feature as far as I know within LFG XLE. Most other approaches have a harder time generating, but with LFG you use exactly the same grammar that you specified for parsing. And what XLE can do is it can reverse the process. It can say for any given F structure, it'll go through and look through the grammar, and it'll go look through all the available rules, and it'll figure out what the possible output is. There might be more than one output, but it can figure it all out. Okay? And interestingly, it can also work with underspecified input. This is actually what's happening in the case with the ungrammatical input, when there was a missing be or a missing to, or the subject-verb agreement was not there. What you can do is you can say, okay, do that again. So we've got this F structure, right? And it's the ungrammatical missing to. What we can do is we can click on this commands window here, and we get a drop-down menu. And what we can say is, please generate from this F structure. This F structure is missing some information, but please generate from it anyway. So what happens when we do that? I'll show you that when it's called up in the command line, because that's actually where it happens. So taking a step back, this is what XLE looks like when it's called from a command line. You will be seeing this a lot as you're loading in XLE. What you do is you type XLE into your shell, and then it'll say something like XLE loaded, and this is actually the 2009 version, because that's the version that works with all the demos that I have. And it's loading this grammar, the call grammar that we have, and it registers, it tells you how many rules it has. And this, sort of as an aside, is an interesting point. What you see here, the rules are translated into states and arts and disjuncts. This means that the grammar is actually translated into a finite state machine, which is one of the reasons why it's so fast. Okay, so this is what it looks like when the grammar generates from an F structure. So we can do something like regenerate, or press that button saying generate from this F structure. They hope graduate in June. It'll parse it. It'll tell you two solutions with a star, which means that this is ungrammatical. So it's found two solutions, but they're both ungrammatical. And then what it does is, very unspectacularly, it gives you the right sentence back. It says they hope to graduate in June. So this is what it's done. It's generated. It's gone through, it's parsed it, it's made the trees, it's made the F structure, it's figured out that the F structure is ungrammatical, and then it's used that F structure as input, put it back into the grammar, and figured out what the corresponding string would be that is correct. And that's what is there. And that all took 0.12 CPU seconds. Okay, an extremely impressive system about how much is being done there in how little time. We haven't pursued this work, mainly because of lack of time, but I think there's a lot of potential there for deep grammars to be used in these call type applications. Okay, did that. Just as finishing off this topic, I'll show you about paradigms via underspecified generation. So next is an example in which the grammar has been asked to generate without any tense aspect information. So we've asked it to parse a sentence, John sleeps, and we've said throw away whatever you knew about tense aspect in this example. So throw away anything about tense present or whatever. And then regenerate. And the result, when you regenerate from that underspecified input, is the entire verbal paradigm of the language. So here's the example. So what we've said is regenerate John sleeps, and I've told the system before to please throw away any tense aspect information it has while it's parsing. So it parses John sleeps, it throws away its tense aspect information, and then it goes through the grammar in the absence of any tense aspect information. And it says, okay, well, what could it be? How could we say John sleep with all the tenses and aspects? And what you get is John will sleep. Where's that? There. John will have been sleeping. John was sleeping. John had been sleeping. John will have slept, John had slept, John sleeps, etc. So you get all of it. So in English you don't get that many, but you get the entire paradigm. So what you can do very well for call applications too is to generate these kinds of paradigms. And that all took 0.09 CPU seconds, all that work. Okay, more call potential. The following is a demo based on work by Melanie Zeiss, who did her PhD at the University of Konstanz, and she worked on an Australian Aboriginal language called Murin Pata. She did some theoretical work, but she also built a system which uses the large LFG grammar again, the one that we've seen a lot already. An LFG grammar and a finite state morphology for Murin Pata. She built these herself, so she built herself a finite state morphological analyzer for Murin Pata, not a trivial task. She built herself an LFG grammar that was not as hard because Murin Pata has more morphology than syntax. And she used the XLE XFR transfer system for machine translation. I'll be telling you about that in one of the last lessons. And she wrote some proscripts for the Tickle TK interface. Okay, so this is what it looks like. Here's where you can read about it. That's one of the places you can read about it. You can also read about it in her dissertation. And here's what it looks like. So you get a welcoming panel that says welcome to the Murin Pata electronic resources. And this collection of programs is supposed to help you learn and understand Murin Pata, this language spoken in the Northern Territory of Australia. And then you have several options. So you can learn more about the system first, about Murin Pata, where it's spoken, what the type is, etc. You can use the English to Murin Pata translation system. That's in fact what we will be doing. There's also Murin Pata to English dictionary, where you can just look up words. Somebody says some long word to you, you can try to figure out what it is in English. And a phonological form checker, because there's quite a number of phonological stuff going on in the language. Okay, so let's look as an example at the English to Murin Pata translation system. So I've clicked on this button. What do I get? I get a window like this that says which English sentence do you want to translate? And then I can click on translate. So I typed in the girls saw the boys and I clicked on translate. And what I got is not the translation. What I got is a number of questions, because it turns out that Murin Pata is very particular about certain amount of information that English is not. So in Murin Pata you need to know, is the subject, girls in this case, a group of 2, or a small group, or a bigger group, over 10 people. Okay, and I've clicked on, I said, okay, this is a group of 2, it's 2 girls. And then I get another question. It says, are they siblings? And if you're not sure what siblings are in this language, you can click on what are siblings. And then you get this information. Siblings are considered your brothers and sisters, but also the children of your mother's sisters and the children of your father's brothers. So you can think about that, whether these girls are siblings or not. And in this case, I decided they are siblings. I said yes. Okay, once I click on that, what I get is this whole big window. So I've answered all these questions up here about the subject, the girls group of 2, their siblings, yes, and now I get the question, is the object a group of 2 people, a small group, 3 to 10, or a big group? Okay, so just for fun, I'll say it's a small group. Again, I have to answer the question, are they siblings? This time we'll decide, no, they're not siblings, these boys. Then we have to answer the question, are they male or female or mixed? So more questions. So in this case it's boys, so they're male. So let's click on that. And then we get the translation. Okay, here's the translation result. So the English, the girls solved the boys, and I'm not going to read the Morin Pata to you. The big thing in the middle is the verb. And there's an alternative way of saying that with less morphology. And if you have only the verb, basically they saw them, then it gives you that information too. Okay, now you've got all this information about, well, you've got the translation, but you might want to know more information about this verb. So you can actually click on more info, and then it gives you a lot of information that you could get. You could get dictionary entries, you could get morphological information, you could get all the possible tenses in the way that I showed you before with the English example, John Sleep. You can do exactly that here. Subject numbers, object numbers, etc. So I clicked on Get Morphological Information. And then what you get is a whole bunch of information about classifier systems, subject information, third person dual siblings, non-future tense, etc., etc., etc. I won't go through all that. What I will show you is you can click on this show form with all possible tenses as well, and what you get is the paradigm here, and this is all the verb forms in the different tenses: non-future, past imperfective, future, future arealis, past arealis. So the application is meant for Morin Pata is unlike most of the Australian Aboriginal languages that you have. It's actually not dying out. It's being learned by children. It's alive and well, and you get a lot of health workers and social workers, etc., coming into the region to work with these people. And for them it would be interesting to be able to say a little bit in Morin Pata, but as you can see, Morin Pata is not an easy language to learn. It has a huge amount of morphology, making distinctions that English speakers haven't even dreamt a language could make. So the idea really here is that what you would do is you would give people these electronic resources, so when they're in that area and they're trying to figure out how to say something, they can type it in, they can figure out the pieces of the morphology, they can get some help, they can look up stuff in the dictionary. So this is really the idea of this application here. Okay, so what we've seen is that deep grammars have great potential with respect to NLP applications. We saw question answering applications, we saw call applications, I talked about tree banks a little bit. They can serve as a systematic tool for language documentation. I haven't talked about that as much, but if you are analyzing a language, and if you put the rules that you figured out about this language right into an LFG system, what the LFG system gives you for any sentence that you type in, it gives you what the analysis is. So it's a very systematic way of actually documenting what you've understood about the language. And the question then is, well, if it's so useful, then why aren't more people using them? Well, there are disadvantages. They're time-consuming and expensive to write. I told you the English LFG grammar, which is very large and very robust and extremely useful, it has been used for industrial purposes, took about 10 years, one person working on it steadily for 10 years, and now it's there. So that is expensive. On the other hand, it's there and it's extremely useful. Shallow parsers, in contrast, can be induced automatically from a training set, and people like to do that, but the problem there is that somebody has to construct the training set first, and what is not factored into this equation is that things like the tree bank, the pen tree bank, which a lot of the English shallow parsers can learn from, or other corpora, they were expensively built by somebody else first, taking 3 or 4 years of development time. and then it takes another couple of years to do shallow parses. So it's not actually clear to me that it's that much cheaper to do shallow parses, except especially for languages which have very few digital resources to start with. Deep grammars are brittle. They have tended to break down when you give them ungrammatical input, though as you can see one can deal with that nowadays. Shallow parsers tend to produce something for everything, so they tend to give you some junk. If they don't know what to do with a sentence, they'll give you some junk, so you have something. Whereas deep grammars tend to be a bit more finicky. Deep grammars are massively ambiguous. Shallow parsers tend to be able to rank the outputs depending on how they've learned, preferences that they've learned from the corpora. And deep grammars have tended to be slow in comparison to shallow parsers. They are very, very fast. I did show you that, that the question answering system, for example, was quite fast. So the disadvantages here are also more about how deep grammars used to be. And this slide is about, well, why pay attention now? And that's because there's a new generation of large-scale deep grammars, which are actually able to be robust. In the LFG grammars, we've integrated chunk parsers, fragment grammars. You can integrate optimality theory, you can integrate rankings, etc. And you can have, as I showed you for the English call grammar, you can allow bad input, but you can then also make good output. So they're much robuster than they used to be. Ambiguity can be contained by, or can be dealt with by the integration of stochastic methods, preferences, etc. So you go through corpora, you figure out what the statistical preferences are for that language, and you can integrate those directly into an LFG grammar. And you can use something called optimality theory, which was developed in theoretical linguistics, to actually rank or pick alternatives. And this is actually what we use for the English call grammar, and I'll tell you about how we use optimality marks or OT marks as part of the LFG grammars in one of the lessons. Speed, things are getting closer to shallow parsers. The demo for the question answering bridge, the system is really, really, really fast. The English grammar is really, really fast. PowerSet used this technology in industrial applications. They're getting comparable results to shallow parsers. They're still a bit slower, but not that much slower. And the accuracy and information content is, of course, far beyond the capabilities of any shallow parsers. So it's well worth it, actually, if you need that kind of deep information, to invest the time. Okay, so now some background of XLE at PARC. XLE was developed at PARC, at the Palo Alto Research Center, as a platform for developing large-scale LFG grammars. LFG itself was invented in the 1980s, so that's now about almost 30 years ago, by the main inventors were John Bresnan and Ron Kaplan. Ron Kaplan was at PARC for many, many, many years and pushed through the development platform, etc. One of the nice things about LFG is that it's theoretically stable, so you can go back and you can read the early papers, say the paper on control and complementation by John Bresnan in 1982, and that's still basically there have been a few discussions, but those results still stand. So it's not one of those theories that changes every 5 years and then you have to change the implementation, but it's theoretically quite stable. There have been improvements, but incremental improvements, and that has also meant that the implementation is very, very solid. The implementation is mathematically very, very well thought out, so it has a very solid mathematical foundation, which means that it's implementable, efficient, etc., etc. And it's also easy to use. If you know LFG, it's very easy to move to XLE because it's basically using the same language. XLE itself is implemented in C, I think C++ these days, generally used with Emacs, and has TK windows. I've been showing you those. It includes a parser, a generator, I've talked about that, and a transfer system, which I've also shown you with the Murin-Pata system. And we'll talk about each of these systems in more detail as the course progresses. There's extensive online documentation. I'll point you to that in the exercise. Here's some background literature that you should know about. So the first seminal work, 1982, The Mental Representation of Grammatical Relations. There's a textbook by Joan Bresnan in 2001, Lexical Functional Syntax, which has some incremental advances that she talks about. There's another textbook by Mary Dalrymple, Lexical Functional Grammar. And there's something called the Grammar Writer's Cookbook, which was co-authored as part of the Pargram project, which I'll tell you about in a little bit. And for this course, these last two are the most relevant. So if you can acquire them, do acquire them. The Grammar Writer's Cookbook is now available as an ebook as well, so you should be able to get that. Okay, so XLE and LFG and Pargram. XLE has been used to develop a number of grammars for very different languages, and that's all been done as part of the Pargram, the Parallel Grammar Collaborative Effort. And there's websites, etc., that I'll point you to in the exercises as well. And there's wikis for Pargram for how to start your grammars, pointers with certain constructions, etc. The Parallel in Pargram is the idea behind Pargram is that we got together and wrote grammars for very different languages, things like Indonesian versus English versus Urdu versus Wolof, and versus Welsh, which is verb initial. And the idea was to analyze all these languages to a degree of abstraction that reflects the common underlying structure. So for everything you want to identify what the subject is, what the object is, the tense, the mood, etc. But even when you do this, there's usually more than one way to analyze a construction, and you can fight about theoretical analyses, but even if you've settled on the same one, you could implement it in different ways. And so what we've done over the years, Pargram has been running since 1996 or 1995. That's over 20 years now. What we've done is we've met regularly once or twice a year, and we've discussed analyses, agreed on common analyses and implementations. And there's something called a feature committee, which has tried to come up with common features across all the grammars. And that's all documented online and in the wikis, etc. Okay, so analysis at the level of C structure, so linear order, surface structure are allowed to differ. There's clear variance across languages. Analyses at F structure, we try to hold as parallel as possible. Right? That's where we think is more of the cross-linguistic invariance. And the theoretical advantage is that this models the idea of that there's the fact that there's universal principles underlying how languages are structured. Not all languages function the same, but the idea is that there's some principles which tell us how these languages are working, and these are what we're trying to capture as well. And that translates into an applicational advantage where machine translation is made easier. So applications are more easily adapted to new languages is the idea, and there's been some work on porting Korean grammar or Chinese grammar from Korean, etc. So that has actually also worked. The languages we've gotten so far are Arabic, Chinese, Danish, English, French, Georgian, German, Hungarian, Irish Gaelic, Indonesian, Japanese, Malagasy, Murin Pata, Norwegian, Polish, Setswana, Tigrinya, Turkish, Urdu, Welsh, and Wolof. So if you know anything, these are a diverse set of languages from very diverse sets of language families. There could be more, but these are quite a lot. And it keeps growing, so the Pargram effort is still growing. It's a very loose organization. We have no common deliverables, but we do have common interests. There's a recent multilingual effort where we're trying to bring together the output from all these grammars, the Pargram Bank, and you can read about it in that paper down there. And many of the grammars are available via the INES website, which is a tree banking website. I'll point you to that in the exercise. The link will be available in the exercise. And what you should be doing is you should go to that website and play with it. So this is the last slide. This concludes today's lesson. So we've basically done motivational stuff and background information. And as the practical part of this lesson, so you should now go off and do some work on your own, is for one, you need to install XLE so you can use it for the exercise coming up in the course. I'll be providing you with sample grammars, and you need to be able to work with these grammars. But the very first step is that you need to install XLE on a computer that you can use. And then second, you should go to the ENAS website where many of the pargram grammars are available and experiment with them. Just see what kinds of parsers you get, whether you understand the parsers, whether you think the parsers are correct or whether something surprises you. So these are the two things that you should do as the lesson today. And as a hint, the English LFG grammar, as I've been saying, is particularly large and robust, so it's worth playing with that one more than the others. But if you know the other languages, play with those and see what comes up. And as I said, all the detailed information and the necessary links I'll provide separately in the exercise file for this lesson. Okay, and that's it for today. See you in the next lesson.